أهلا وسهلا بكم أعزائنا المتابعين في SBE Student بصرة شابتر. يقدم المهندس عبدالرحمن جرادة في شابتر جامعة البصرة محاضرة بعنوان Fundamental of Reservoir Engineering، مختصر عن الخبرة العلمية للمهندس، متخصص في هندسة المكامن ويعمل بهذا التخصص لأكثر من 6 سنوات. يعمل ولديه الخبرة في مشاريع خطط تطوير الحقول وإعادة تنشيط الأخبار المغلقة في حقول شمال أفريقيا. حاصل على الماجستير في هندسة النفط والغاز من جامعة بوليتكنيك في مدريد. عمل 4 سنوات في شركة أكاكوس أويل أوبريشن. يعمل الآن في شركة برجن. سوف تكون مدة المحاضرة 1.5 ساعة وآخر 15 دقيقة مخصصة للإجابة على الأسئلة المطروحة من قبلكم في التعليقات. أنا علي فليح، أحد أعضاء شابتر SBE. أتقدم بالشكر للمهندس عبدالرحمن على حضوره وقبوله الدعوة نيابة عن بقية أعضاء شابتر جامعة البصرة. أهلا وسهلا بك مهندس عبدالرحمن، تقدر تتفضل.
السلام عليكم. Actually, thank you for the introduction. I'm afraid that this presentation is going to be in English. So because like there are some like non-Arabic speaker, they are joining us, so it's going to be in English. At first, please let me know if you can hear me and see the screen very well.
Yes, it is good.
Okay, perfect. So thank you everyone for joining this presentation. Actually, thanks to Basra University, specifically SBE student chapter for setting up this session. And today's session is going to be about fundamental of reservoir engineering. Actually, this presentation was made for non-reservoir engineers, so and also for students that would like to know how it looks like being a reservoir engineer and why reservoir engineering is important to oil industry in general. So you might find some, basic theory. You might find some, basic or foundations of reservoir engineering concepts. But by the end of this presentation, I will touch and I will go in some advanced reservoir engineering as well. So starting with the table of content, I'll start with the introduction of what is reservoir engineering. Then we will see what sort of reservoir types we have in oil industry. And then I choose a couple of topics that somehow related to, reservoir engineering, since they are considered to be the essence of reservoir engineering, such as special core analysis, which represents the core or the rock properties, and then I will talk a little bit about the fluid property, and finally ending up with the main theory or the idea behind the well testing and how well testing can be a valid tool to characterize the reservoir. So before I start talking about reservoir engineering, let us zoom out and define what is petroleum engineering. Actually, petroleum engineer's job is to find, to drill and explore for oil and gas and rock formations deep into the earth. So as a petroleum engineer, you can work on many different areas. For example, there are some drilling, production, and reservoir engineering. So for drilling engineer job is to to be out there on the rig and supervising the drilling of the borehole deep into the earth to access the rock formations that contain that oil and gas. So the drilling engineer is responsible for preparing that well to be placed on production, and once that task is completed, so the person's job is actually done, and after that, at that point, the production engineer takes over, and the production engineer's job is to figure out which rock formation that has oil and gas in it. And also to figure out the most effective way to produce that oil and gas, and produced all the way up to the surface. So these are, starting with the drilling engineer, and then goes to the production engineer. And then the third area is the reservoir engineer. Actually, reservoir engineers are really responsible for, evaluating the quantity of that oil and gas down into the reservoir. So basically, as a reservoir engineer, we do a lot of calculations, we do a lot of studies and reservoir simulations, trying to simulate how oil and gas are flowing into the rock. I mean, amongst the porous media. So we get, the optimum strategy to get that oil out to the surface. So and this, are different techniques are usually applied to, to extract that oil, which means, for example, the proposing additional drilling wells also can mean, flooding the formation with the water or carbon dioxide that helps to enhance the recovery of that reservoir. So briefly, these are like the main branches or the main domains of petroleum engineering. So now let's go a little bit in details into the rules of reservoir engineers. Actually, the main rule is to evaluate the well and reservoir data and make, the best prediction possible to help determine the recovery potential, and therefore you evaluate the commerciality of a field. So generally, the reservoir engineer can be called upon the technical team at various points in the field life. For example, as a reservoir engineer, we can be involved, before the well is even drilled. I mean, during the exploration phase, actually to help evaluate the prospect. So you can see that we can be involved even of the drilling process. And also we can, the reservoir engineer can be involved after the field has discovered, actually to determine the reserve of the field and plan its development strategies. And finally, the reservoir engineer can also be, work on mature fields to maximize the recovery of the field, looking for like recompletion opportunities, for example, controlling the water production, maximizing the oil production, monitoring the reservoir pressure, which is called as a non-associated gas. So this is like the first type of reservoir, which is like a gas reservoir, and we have mainly the gas production. The other type of reservoirs is the oil reservoir. This oil reservoir primarily produces oil, and the gas is produced from an oil reservoir is called an associated gas. So initially or primarily there is oil production, but there is some sort of gas that is associated with that oil. So in such kind of reservoir, we name it as oil reservoir. So based on the fluid or the produced hydrocarbon, we have gas reservoirs and we have oil reservoirs. We will see in the PVT what sort of type of fluids that we might have, and there are another type or more than two type of reservoirs, like a mix between, there is a gas reservoir and there is an oil rim, a thin oil layer that, located beneath the gas zones, and we will see that, in the fluid property part. So as part of creating the total in place, okay. Just do you see any changes in? Oh yeah, now you can see the change in the slide. So here I'd like to talk about the volumetric calculations that we usually do to estimate the oil in place. For example, the recoverable oil and gas reserves, must be estimated in each reservoir. And of course, there are a bunch of techniques that we usually use to estimate the in-place or the hydrocarbon. And one of the basic methods is the volumetric method. And the data that we need to estimate the in-place in volumetric, as you can see here, there is porosity, water saturation, net bay thickness, area, and formation volume factor. So starting with the porosity is like the fraction of the void space within the reservoir rock that is, available for the storage of that fluids. So it's like a container for our fluid into the reservoir. And basically, there are two types of porosity. We name them as primary porosity and secondary porosity. For the primary porosity, it actually refers to the porosity that was performed when the reservoir was deposited. I mean, when the deposition was, formed at that time. So it's like considered to be as initial porosity. But in many of the reservoirs or many of the depositional process, there is something called diagenesis process. This diagenesis process usually alter the primary or initial porosity. And this alteration could be an increase in the primary porosity, or it could be decreasing the primary porosity. So we have primary porosity and the secondary porosity. The secondary porosity, as it all refers to the space in the formation rock which created by geological process after the formation had been deposited. So after the diagenesis process. And for example of secondary porosity, we have like a vagular porosity, which is like a huge or like usually it increases the primary porosity. And another example is the fracture porosity. All these kinds, usually they came as a result of a diagenesis process as a secondary porosity. And then we have the water saturation. In fact, let's go back before the oil, migrated into the reservoir. So the porosity initially was filled by water, and the water was later, displaced by the hydrocarbon. So this is, occurred during the migration process, and what we called as a drainage process. Now the question is the hydrocarbon, will be occupying the porosity like 100%? The answer is no. Why? Because part of initial water saturation would remain in the porous media, and will not be displaced by the hydrocarbon for many reasons. One of these reasons is the capillary force that is required to do the displacement process. So because of that, there is a portion of water will remain in the porous media, and this is what we call the initial water saturation, which is the percentage of rock porosity that is occupied by water at initial conditions, or at least at the time of the discovery of that field. So now we do know what is the initial water saturation that our field exists, and why we need to know the initial water saturation. Basically, the oil saturation is going to be the balance of that saturation. What I mean is SO, or oil saturation, is going to be 1 minus SW, which is the water saturation. So if you take a look on the equation that you can see, once we produce the oil, are we going to produce all that oil that exists in the porous media? The answer again is not going to be yes, is no. Why? Because under best conditions, there is portion of oil will remain in the reservoir, and this is what we call a residual oil saturation. So there is we do have in our system the initial water saturation, which is the water that could not be displaced initially by oil, and there is another thing which is residual oil saturation, which is the saturation of oil that cannot be extracted, cannot be produced. Okay, so what is the oil saturation? It's, I told you, the amount of hydrocarbon that left behind in the reservoir, and when the relative permeability, why there is since it was able to enter to that porous media, why is not possible to get out of that porous media? The answer is when the relative permeability of oil become zero. So at that time, the oil will not be able to move on and to be extracted. So there is residual oil saturation and there is initial water saturation. And in the next slide, I will spend some time talking about what is relative permeability and the main theory behind. And then we do have net bay thickness. For the net bay thickness is actually is the measurement of the thickness of the reservoir that contains oil or gas. And because of the variation in some properties within the reservoir thickness, we actually exclude what we call them as a non-pay thickness. For example, let's imagine we have a reservoir, which is a sandstone reservoir, and there is kind of interpreted by shales. These thickness or these intervals of shales are not considered to be as a reservoir. So basically, we just remove them in our calculations, and they're not considered to be as part of the reservoir. And then there is the area. The areal extent usually of hydrocarbon, like most of the time, is determined by a combination of seismic data, by well testing, by sometimes we need to drill some appraiser wells to determine the areal extension of our field. So these are the main parameters that needs to be identified to estimate the oil in place. And then we have one important factor that we named as formation volume factor. This factor is actually used to adjust the fluid volume differences between the reservoir and the surface, because the conditions of the reservoir is completely different from the conditions at surface, and the hydrocarbon and the oil that we sell it to the market is not in the reservoir condition. Obviously, it's in a surface condition. So we use this factor to convert the condition, to convert the reservoir condition and convert it to the surface condition. So now, actually, you have learned a very important physical parameters that are used to characterize the reservoir, which are the permeability, the porosity, saturation, and sort of fluid property, which is the beta O. Here in this equation, the original equation of oil initial in place, as you can see, it's about like we are calculating the total volume, which is the area multiplied by net bay thickness, and then this total volume we only interested in the pore space of it. We are not interested into all that volume, so we multiply it by porosity. And for that pore volume, we are not interested in water saturation. We are only interested in oil. So that's why we do 1 minus SW, or 1 minus water saturation. And then we subdivide it by, we divide it by beta O, or formation volume factor, to convert that volume into, or convert that in place into the surface conditions. And for that number, 7758, we usually use this number to convert just the unit to make it like to the field unit. So now, if someone would like to ask, do we expect to produce all that hydrocarbon? The hydrocarbon only, we don't expect to produce all that hydrocarbon in the reservoir, but only a percentage of it. And this percentage is called the recovery factor, which is a very subjective number, and it could vary from reservoir to another reservoir. However, by knowing what is the drive mechanism, this can give us a pretty good idea of what, recovery range that we could expect from the primary recovery efforts. So basically, there are 5 drive mechanisms that was estimated by industry. As you can see here, there is a solution gas drive. In the solution gas drive, actually, they are driven by the gas that comes out of the solution as the pressure drops. So this volumetric gas drive for oil or gas reservoir are driven by the pressure depletion in the reservoir, which originates from the expansion of fluids that exist in the reservoir. The other type of drive mechanism is the gas cap drive. In the gas or in the oil reservoir that produces by gas cap expansion, which helps to maintain the pressure. So as the oil is being produced from the reservoir, the gas cap expands and pushes the oil to be produced. So it provides additional energy for oil to be produced. And we usually enhance some sort of reservoirs by injecting gas into the gas zone. So we make sure that we make sure of the stability of the gas support that is coming from from gas cap. But in reality, actually, in some fields, we find out that gas is an energy. So it's gas equals money. It's not always we need to use as energy, but also some companies, they are producing that gas cap. In such cases, we might end with, it's like a pure technical example. In some fields, there is an oil rim or an oil layer that is beneath the gas cap, and once you start producing from that gas, you're actually using the energy of that reservoir. So you might end up of like decline in reservoir pressure, and losing this energy, you might not be able to extract that oil. I mean, the oil doesn't have any or doesn't have enough pressure to be produced. So monitoring such reservoirs that has original gas cap is really critical in most of the cases, and it requires long-term strategies and long-term plans to maintain your energy, and also to increase the recovery for as long as possible in the field life. And another type of drive mechanism is the water drive mechanism. This is one of the most famous types of drive mechanism. The oil, as the oil, reservoir produces from the pressure support that is provided by the aquifer that is getting into the reservoir as the oil is getting produced, which can enhance maintaining the reservoir pressure. And how can we maintain or support this kind of drive mechanism? Is actually by injecting fluids, probably water, into the oil or even water zones to maintain the pressure and increasing the sweeping efficiency. Basically, if when the drive mechanism or when water drive is not enough, alone is not enough to maintain the reservoir pressure, we tend to do some injection projects to maintain the reservoir pressure, and deciding which area, which intervals we need to inject. Do we need to inject in an oil zone, or we need to inject in a water zone? The main difference is when you are injecting in the oil zone, that you are not only providing support, but also we are increasing the sweeping efficiency of that reservoir. But sometimes is getting tricky. Why? Because when we are injecting water into the oil zone, and as you know, oil has more mobility or higher mobility than oil, so we might have an early water production, which is the least thing that any reservoir engineer would like to see in reservoir monitoring. So optimizing the process and maintaining the reservoir pressure, this is again, it's something is considered to be the essence of reservoir engineering tool, reservoir engineering role. And then we have the gravity drainage drive mechanism. Usually this exists in a tilted reservoirs where the gravity force helps somehow to produce that oil. This is not really common as much as water drive mechanism and solution gas drive. And sometimes we might end with a combination of all different drive mechanism. We do have water influx from the bottom, and we do have gas cap from the top. There is a gas solution expansion, of course, while production. So all these could coexist together in one reservoir. So now, by learning what type of reservoir you have, then you can develop your field and make the optimum strategy to extract that oil for the long term, with a long vision, and of course with the most effective economic way. Here, the special core analysis, actually I wanted to talk about the special core analysis because basically it's really important of understanding and evaluating and management the hydrocarbon reservoir. And of course, if you have like high reliable data, will allow us to maximize the performance of the reservoir. And that's actually by understanding different aspects. For example, here we have the capillary pressure. The capillary pressure, where we can, build the saturation height models of the hydrocarbon in place. So as you remember, the water saturation, initial water saturation, is very critical in determining the in place. So how can we determine the water saturation in place? One of the most effective techniques is the capillary pressure technique. So building the saturation height model of hydrocarbon in place determinations, and also the capillary pressure used to find out the best correlation for the pore throat size distributions. And it's quite interesting that the capillary pressure curves provide means to estimate the fluid distribution versus depth, and it's totally independent to the logs, to the saturation that we have from, for example, using Archie equation. So this is the value of capillary pressure. And then we have relative permeability. The relative permeability data is widely recognized for the prediction of oil recovery during the displacement by water. And of course, if you have reliable water permeability data set, and this is actually can reduce the uncertainty of the dynamic reservoir modeling and provide a solid foundation of reservoir engineering studies. And finally, there is wettability. The wettability is actually affects the amount of oil that can be produced at the pore level, and also affects the water flooding performance, and determines how easily water can be injected, and how it moves throughout the formation. For this presentation, actually, I wanted to talk in a little bit details about relative permeability, and of course, we can have maybe other sessions to talk more about the capillary pressure and the wettability. So in fact, deriving the relative permeability is a key parameter for, as I told you, for reserve assessment and, for recovery estimate. And the main application of relative permeability is to control the advancement and control the mobility of different fluids coexisting together in the porous media, and therefore, controlling the recovery of the fluids. So the permeability that we usually measure from cores, they are considered to be as absolute permeability. And what do I mean by absolute permeability? I mean it's only saturated with one fluid. So we have only one fluid, and this fluid permeability is considered to be absolute permeability. But in real life, or in most of the reservoirs, we do have more than one fluid. So from here, we do have a term called relative permeability. Relative permeability is like the ability of porous media to conduct the fluid where its saturation is less than 100% in the porous space. I mean, in the same porous space, there are two different fluids coexist together, and they're trying to, move. The movement is considered to be the relative permeability. And as you can see here in this slide, this is like a typical oil-water relative permeability data. Usually, the experiment is done with, increasing the saturation to simulate the water injection into the reservoir. So here we have the relative permeability on the y-axis, and in the x-axis we do have the water saturation. So and this is the oil relative permeability, and this is the water relative permeability. As you can see that the water relative permeability, or actually the water does not start to move until it reaches at certain, saturation. And this specific saturation we called as a critical water saturation. On the other hand, after this saturation, the water will start to, keep moving or keep increasing as the water saturation increases. On the other hand, the oil relative permeability is getting decreased until it reaches to a point that is called residual oil saturation. At this point, the oil is like cannot move, and this is the SOR, and this is the portion of oil that is not going to be extracted from the reservoir using initial drive mechanism. So these are the main three the main parameters, which is critical water saturation. After that, the water starts to produce, and this is the oil relative permeability until it reaches to residual oil saturation, where the oil cannot move anymore. And this is the relative permeability for for oil and for water and for gas as well. So basically, this is the main parameters that needs to be understood, or the basic parameters needs to be understood. And by the way, when we are doing the simulation modeling, relative permeability is quite essential and is quite important and affecting the construction of our model. Why? Basically, it controls the water movement, and also before that it controls the water breakthrough. As you can see, the initial water saturation is the saturation, or is the value that controls the at which saturation the water starts to show up. Okay. Then we move on to the PVT analysis. For the PVT, it's important to know how the hydrocarbon fluids, change with the temperature, and of course, and temperature and pressure as well. So the PVT is the pressure, volume, temperature relationships with our reservoir is, the reservoir property is getting, changed according to the changes that we have in pressure and temperature from the reservoir all the way up to the surface, or sometimes the changes that occurs during the field life. At the beginning, the pressure is completely different from the end or the depleted part of the field life. So we realize that the reservoir rock is normally saturated with 2 or sometimes 3 fluids, as I told you before, water, oil, and gas, and the relative amounts of these fluids, they actually present their composition and the physical properties. Of course, if we do have a gas in, if we do have oil and gas in our reservoir, the composition would not be the same if we do have an only oil in the reservoir. So the presence of fluid is actually controlling the composition and controls the physical properties such as the phase behavior, the density, the viscosity, the compressibility, which can vary widely from one field to another field, and often from one reservoir to another reservoir. So during the production, the fluids leave the reservoir at whatever its condition at that time, and flow up all the way to the surface. So let's assume that we have a sample of crude oil that we take it and place in a sample chamber and restore its original reservoir conditions in terms of pressure and temperature, and fill it with a mercury bomb, so we can look through the cell window and see what is inside. So at first we are in a point A, which is only liquid that exists in our reservoir. So the green line, the green colors refers to the presence of liquid. Okay, and now if we drop the pressure up to the certain point, we notice that the pressure, we notice that there is suddenly a bubble of gas appears in the crude, and this point is referred to be as the pressure, the bubble point pressure, which is the point where two phases being to be present together. So this is the first point that two phases, gas and oil, are coexisting together. So we started at pressure higher or above than bubble point pressure, and as we drop down to the bubble point pressure, so now we start talking about two different phases coexisting together. And then if we continue decreasing the pressure, you can see that the total volume of gas actually expands, and there is more and more of the of gas volumes are getting occupying the cell chamber. So in fact, when gas first formed, it consisted of a very lightest molecules. This is like at the first bubble point that showed up, and perhaps it's methane. And like now, because of the lower pressure, more and more of heavier molecules moves to gas phase, causing it become more dense and more viscous. And the oil is giving up lighter components to the gas phase, and it also becomes more dense and more viscous. So now we are moving from we have only a small portion of gas that existed, but as the pressure goes down, the more of heavier components is being moved from liquid to gas. So oil is becoming more dense and more viscous. It becomes more of what we call a dead oil. Okay, and finally, well, it's not finally, it's just a step before the final condition, which is once we keep reducing the pressure, we reach to a point where only a small drop of liquid remains. And in this chamber, as you can see here, the green bubble, and this is what we call the dew point pressure, which is the point that we only have like a drop of liquid exists in our reservoir, in the chamber here. And once we drop the pressure even more, okay, so the liquid disappears, and everything is the vapor or in a gas state. So if we repeat this process for different temperatures, we will find out like new bubble points and new dew points for each temperature, and then we can create what we call the phase envelope. So basically, by we can join these points of bubble point and dew points together, creating different lines: the green line and the red line. And these two lines are they will meet at the point called the critical point. So between the curves, when we have two phase regions, at first there's above the bubble point, as I told you, above the bubble point pressure is only single phase or only liquid. But when we reach it, when we decrease the reservoir pressure until we reach it to the bubble point pressure, at that point we have the bubble point pressure, and then we start the two-phase region. In the two-phase region, these are quality lines. These quality lines representing the percentage of liquid. So at first we do have 75% of liquid exist, even though it's like two-phase, but the vast majority of that phase is liquid. And as we go down, as we remember that more of heavy molecules is being converted to the gas phase, so liquid is getting decreased and more gas will show up until we reach to a point that is only one drop of liquid, and this is what we call the dew point. And then after that we will have only gas in our system. So this is a very typical phase diagram. Based on that, there are different type of fluids usually classified. For example, there is a dry gas, which is this type of fluid. It's like gas, pure gas in reservoir condition and into the surface condition. There's no any liquid that could exist during the production process. However, in wet gas, it might start as a gas or as a dry gas at surface, but at the reservoir. I'm sorry, but as it moves from the reservoir all the way up to the surface, there's some liquid may exist in our reservoir. And the same thing for oil. We do have black oil, which is there is no any presence of gas. But as the reservoir pressure decreases below the bubble point, we might have something called volatile oil, which, as you can see here, it it ranges from the critical, when the operating pressure system ranges from the critical pressure and the maximum pressure. So at that time, we name it as a volatile hydrocarbon or volatile oil. There are a number of different tests we usually do to characterize the fluid properties. So we want to test the fluid composition. Actually, we need to understand two main parameters in our composition, which they are the C7 plus. As you know, once we measure the composition of that fluid, I mean, it's not possible to measure each single composition in that fluid. In oil industry, it's like possible to measure only like until C30 or maybe more, but it's not possible to measure all these components because of many reasons. Why? Because it's quite expensive to measure like all the exponents. It requires a high technology to measure all these components, and the other thing is not that important to know beyond C30. You know what I mean by C is like the composition. There is several composition, which is C1 is methane, C2 ethane, and until C30. So it's important to understand C7 plus. We name it C7 plus because it's like the summation of C7 until it reaches to all the other type of compositions. So C7 plus and the API of the fluid give us a very good idea what type of fluid we have. Do we have black oil? Do we have volatile? Do we have dry gas and whatnot? Of course, in gas reservoirs, we expect to have very low C7 plus, but we have very high C1, which is methane. The opposite in black oil, we do expect to have high percentage of C7 plus. Then we do flash test, which is going to allow us to define the formation volume factor and the gas oil ratio at different separator conditions. So we're going to have to provide the lab with separator conditions that we are expecting to be considered in the test. After that, there is a constant composition expansion test. This test is actually used to define the properties above bubble point pressure. And so it tells us how the formation volume factor and the viscosity are going to behave when we are above bubble point pressure. So this kind of test is designed to be above bubble point pressure, and if with any presence of gas that exists in that test is not going to be extracted, assuming that there is a solution gas exists into to that oil. So eventually we take the parameters that is above bubble point pressure, but it's not always we are interested only in the above bubble point pressure. In some cases, we are interested even below bubble point pressure. When we are interested in that case, we are interested in such when we have the reservoir pressure below the bubble point pressure. So in that case, it's important to simulate or mimic the fluid change that occurs accordingly to the pressure differences. So we do have a test called differential vibration test. This kind of test that allow us to define the PVT or fluid parameters that below the bubble point pressure. And to understand as we deplete in our reservoir and we take those fluids out, So the gas-hour ratio, and we see the formation volume factor and the viscosity, how it's going to be or how it's going to change as we take off the free gas out of the reservoir. So the main differences between constant composition and differential is the extracting the gas from the chamber or from the test. We take it out in the differential evaporation test to mimic or to simulate the change in the fluid properties below bubble point pressure. And of course, we do have a viscosity measurement. We need to do some sort of viscosity measurements. We do both above and below bubble point pressure, and they're usually done with a rolling pole viscometer, so that this can actually test how the pole rolls through the reservoir, the different temperatures and pressures. So these are the most common tests that we usually do for PVT analysis. And then moving to one of the most interesting topics that any reservoir engineer may have, and this is a very valid tool for reservoir characterization as well, which is the PressureTransist Analysis. It has many names. I'm sorry. Some they used to call it as a well testing, and then some they named as PressureTransist Analysis. So once the well test or PressureTransist Analysis is performed on data that is acquired during dedicated operations called a well test, a typical well test setup is shown here in the right side of this slide. So there are like temporary equipment is installed downhole at surface, and the well is put in production under like predefined program, and a diagnostic is performed to find out some specific parameters. Generally, this is done during different periods. During shut-in period, what we call build-up period, and also in a drawdown period or cleanup period. So the test is being done over stages, starting by cleaning up, which is the first drawdown, and then there is the first shut-in. Usually it takes like half an hour, and then we repeat the process again. We put the well on production again, and then followed by the second build-up or the second shut-in period. So the data that is required to perform PressureTransist analysis are basically the rates, the production rates, the pressure, the reservoir, of course, the measured reservoir pressure in both static and in shut-in and production period, the fluid property data, basically the formation volume factor and the fluid compressibility, the water saturation. These are important or essential input into the well testing. And there are a few additional parameters such as like well radius and the pay zone that is required to be input as well. The main flow regime of interest in well testing is something called infinite acting radial flow. And if you work on well testing, you definitely hear about this, because this considers to be like the main period that is all reservoir parameters is taken from, as you will see in this slide. At first, the PressureTransist analysis methods were specialized. There are some plots basic plots that were used in 1950s, I guess, to identify and quantify this infinite radial flow. And then in 1970, there is a technique called log-log type curve matching techniques, were developed to complement the straight lines that were proposed by the old methods, which is MDH and Horner plots. And then the last technique and the most efficient technique is actually was developed in 1983, which is the derivative technique that was developed, which increased the resolution and the reliability of new generation analysis. So once we receive the pressure test data to analyze it, we can divide the test into separated periods. Starting from Wilbur effect. This like for the pressure transit analysis, anything related to the Wilbur, could be considered as a noise. What I mean is like Wilbur effect, like it spoils the early part of the pressure response, and it may even persist throughout the whole test and even the shut-in survey. So basically, there are two types of Wilbur storage effects. The first is like a constant Wilbur storage effect, which is the simple one, and the other is changing Wilbur storage, actually due to changes in the condition in the Wilbur during measuring the pressure. For example, the presence of gas into the Wilbur leads to having the changing Wilbur effect, which is because of very high compressibility. So that's why these noise at the beginning of the pressure change that really affecting the overall pressure measurement. And sometimes there's a change in the diameter in the completion itself, and the Wilbur leads to change in the Wilbur storage effect. So let me get a step back. I might have jumped one point, which is physically, what does it mean when I say Wilbur storage? Wilbur storage is actually when we are measuring the pressure, we are lowering the pressure gauge down to the bottom of the Wilbur, and assume that the well was cleaning, there is flow coming to the surface, and then we would like to perform a build-up test or a shut-in. We need to shut in the well to perform the build-up test. So once we shut in the well from surface, it takes some time to be felt in the bottom of the well. Because the reservoir keeps moving from reservoir to the sand face to the Wilbur, and at that stage there is pressure. The pressure is getting affected by by not closing the production from the reservoir. So at that time, this is what we call the pressure. The Wilbur storage effect. And there are some techniques actually is used to overcome this issue by performing or by installing downhole valves that perform the shut-in from the bottom of the Wilbur, the bottom hole itself. So there is no gap between, so there will not be any effect for that delay in the reservoir pressure. So this is why we say that the Wilbur storage effect is something not good. Is something may spoil our reservoir measurement. It might affect the reservoir interpretation or well testing interpretation. Generally, in PressureTransist Analysis, reservoir features are detected after well pore effects, and well behavior have ceased and before the boundary effects are detected. This is what we might call intermediate time response. So a part of the well pore effect, now we need to have the real measurement of our reservoir, which is during the intermediate time response. And the main parameter we're looking for is the mobility of the fluid into the reservoir, which is the permeability over viscosity. And when the fluid viscosity is known and assumed to be constant, we can calculate the permeability thickness product. And this is what we named as a KH. And this is one of the most important parameter we gain from well testing, which is the KH. And we take it when we are sure that the pressure response is like considering the reservoir is not actually affected by the well pore storage effect. So whatever the variant, this result will be quantified by the pressure match of the log-log plot. There are different type of reservoir models we might have. We have a homogeneous reservoir model. We might have a double porosity model, double permeability model, and there are many other reservoir models we might have. So the one that you see, the figure that you see here, is actually belongs to a homogeneous reservoir model. So let's find out what is homogeneous reservoir model looks like. Okay, so the homogeneous model, when we characterize the reservoir to be as a homogeneous reservoir, is actually we are assuming that we are having the same reservoir property along the whole reservoir system. So homogeneous reservoir is like a simplest possible model that assuming everywhere the same porosity, the same permeability, and the same thickness. So this is the main assumptions for pore. So that's why we do have different signature of double porosity than homogeneous reservoirs. In homogeneous, we do have a straight line that is describing, the radial flow that occurs from the matrix itself. But in the double porosity system, we do have another signature. So that's why the double the derivative plot is actually very descriptive plot that can tell us what sort of reservoir do we have. Is it double porosity or an homogeneous reservoir? Another example of heterogeneous reservoir is like the double permeability as well. So we do have double porosity and we do have double permeability model. When different productive layers has the same rock properties, it's considered to be as a homogeneous reservoirs. However, in the double permeability model, it's assumed to have like the reservoir consists of two different layers with different permeabilities, and each of these layers is like either perforated or not. There will be a cross flow between the layers, and this cross flow is like function of the differences in permeability. And each each layer has got its unique permeability, and as long as there is pressure differences between these layers, so there are going to be different. Each layer will have different pressure, different permeability, and this is going to affect the total, the overall, the presence of different layers is giving different signatures that have different well testing results. So each model has its own signatures and could be identified by derivative plot. And finally, the latest period, and we can go again back here to the example of radial flow. For the latest period, we can identify the boundary of the reservoir. In most of the well tests, the first part of the pressure response is dominant by well bore effects and flow diffusion immediately around the well. This is like the first the pressure measurement, and then most of the cases, but it's not always is the case. The middle and the late time pressure response, will be dominated by infinite acting radial flow, which is the characterized by the stabilization of derivative, where we measure the average permeability in our that represents our reservoir. And the permeability that we measure from well testing is considered to be as the effective or the average effective permeability. Some people actually, they try to compare the permeability that is obtained from core data and other permeability that is obtained from well testing, and this is actually a wrong approach because they are not they are not considered to be as the same category. In other words, the permeability that we take from core data is considered to be as an absolute permeability, but the permeability that we gain from well testing is an average effective permeability. In my point of view, the best source of data that you have for permeability, even though it's quite it's a subjective parameter, but the best source of data that you may have the permeability is well testing, because it goes beyond the vicinity of the well bore. It reaches to the reservoir, and sometimes it reaches to the boundary of the reservoir. So this permeability is considered to be the average effective permeability, rather than the one that we take from cores that it takes that's considered to be as an absolute permeability, and also we take only a small portion of nearby the well bore, which might not represent the whole reservoir. So this is pretty much thing that is important to understand in terms of permeability. So once we reach once the reservoir at first reaches it feels the well bore effect, and then it reaches to the reservoir. After that, if there is enough time, if the test was long enough to reach the boundary, there is another signature that could be raised when the boundary just show up. So generally, there are different types of boundaries that may exist. For example, there are faults. They could be like a single fault. They could be intersecting faults. They could be parallel faults. Sometimes it's important to to distinguish between the fault and the imaging well, what we name it as an imaging well, because you need to understand in well testing, you need to understand what is going on around this well. Is there any wells that is put in production? So if there is a well put in production, so this could have an effect on the well testing, and you might think that there is a fault, but in fact it's not a fault. It is the imaging well. So the boundary is good to have an idea if there is any faults, if there is a single fault or intersecting, and also the distance from well to that fault, and then we can compare it with the one with the seismic, and of course the resolution of seismic might not be that accurate. So such kind of analysis that we usually do to end up with a table that summarizes all well testing data, mainly the permeability thickness product, which is the KH, or the deliverability, and of course some well parameters like the skin, and we can track the skin over time, just in case if there's any damage that may occur while production of the field. So I think this is all for today's presentation. I tried to make it very simple as much as I could, but it sounds like when it comes to well testing, it's a little bit tricky because this is a very huge topic, and obviously it's an important tool for any reservoir engineering, for reservoir characterization aspect. Yeah. Thank you for your time. Thank you for listening. And of course, if you do have any questions, you're welcome.
Mr. Abdulrahman, thank you on behalf of myself and behalf of Student Basra Student Chapter. I would like to thank you, and thank you for presenting this lecture and sharing a bit of your experience with the students and your knowledge on reservoir fundamentals. Thank you very much. And أعزائي الحضور, if you got a question, you can type it on the chat box, or you can open your mic and type a question.
Okay, thank you.
Assalamu alaikum.
Wa alaikum assalam wa rahmatullah.
How are you, Mr. Abdulrahman, excuse me.
Hello, Muhammad.
Actually, I'm very excited about your language, and I am very grateful about your effort to studying us English language. And if you don't mind, I have a little bit tiny recognized about your accent, because you're actually mixing about British accent and American accent. If you observe that, am I right?
Well, actually, it's kind of something in between. Yes, something in between.
But I'm very grateful. But I'm actually very grateful about your studying and thinking all about that efforts for studying us reservoir engineering. But my question is not about that lecture, but about that reservoir engineering, if you don't mind.
Yes, please.
My question is actually, how do you identify the type of drive mechanism in the reservoir? For example, there's three type of drive mechanism. You say water mechanism and aquifer, and there's actually gas solution and another one, I forget it actually. But the main question is, how do you identify the type of drive mechanism of the reservoir when we are producing the oil?
Okay, yeah. Well, actually, understanding the drive mechanism is something very essential to understand. There are a couple of techniques we do to examine or to characterize the drive mechanism. Before I start talking about this, is actually we don't invest too much money about understanding the aquifer parameters. For example, we do not drill a well just to understand what is the aquifer permeability, what is the, for example, the extent of the aquifer. We do not spend too much money about that. So what we do instead, actually, we use the material balance to identify all sort of energy you have in the reservoir. So as a simple exercise, you try to build a material balance model. We usually use I don't know if I'm allowed to say some softwares, but there is some softwares that you can build your reservoir model. You can start with a single, we name it as a single tank, and that single tank you can it requires the PVT data, and it requires the production data, and also it requires the water aquifer data. For the water aquifer data, it's something unknown and you don't have. So at that case, you just simply run after establishing your model. So you try to do the calculations, assuming that there is no aquifer influx, and you will see how the model that you extracted compared to the actual data, which is, for example, one of the things that you need to match is the analytical approach or the analytical method. So the solution gas-oil ratio, which is involved. So if there's a mismatch, so in that case, it proves there is water influx, or so mismatch start with no water influx, and we check our model how it's going to behave. If there is a big mismatch between them, so at that time we need to tune the aquifer parameters, and we check at which parameter that do we need to have a strong aquifer to get the match of the observed data, or sometimes we need to have a very weak parameter of aquifer to match the observed data as well. So by the end, you can have an idea about which drive mechanism that is dominant to production. But I can tell you, if there is a water influx in your system, this is going to be most likely the most effective, the most dominant aquifer, because other energies or other drive mechanisms, they usually disappear when it comes to water influx or water drive mechanism. So and if there is, and if in the case that you don't have the water drive mechanism, it should match with the the PVT property that you used to build your model with, which should be considered in the PVT. So if you got a match without water influx, in that case you don't have an aquifer. So you start to do whatever injection process or something. Generally this is the main approach that I use to follow to identify what is the strength of the aquifer, what is the the main parameters that we usually adjust to have the match between the observed data and the constructed model is the encroachment angle. So in which direction the aquifer is coming from? Is it coming from 360 degree? From all directions, or only part of the field that is expect to have some water production? This is like a general technique. We start with a single tank, building a single tank, and try to match the observed data using analytical method. But in some cases, we need to divide the reservoir into different tanks. Each tank represent. So hopefully that was an answer to your question.
Thank you, sir, for your effort. But it's actually I got this so complicated. Complicated is actually according to your speak. But that I got from you that the most important thing is PVT and material balance. But the main problem is that we not got the material balance in our college. But in the first department we're gonna take it. But the PVT, I don't know, but I know there's a app, I guess, the application in the laptop about it. But we don't know use it actually. But if you can, I hope you present something about the PVT application.
You mean the PVT software applications?
Yes, exactly.
Okay. Yeah, I'm not sure if. As you know that I'm working for Schlumberger, so all these softwares, any presentations should or require previous approval of the company and whatnot. So I will check what I can do, and of course I will share with you if it's possible, of course.
Thank you, sir, for your efforts.
Yeah,
and I'm grateful for you.
You are welcome.
Mr. Abdulrahman,
excuse me, sir. May I got your number for any questions if I had? I'm sorry for interrupting you, Mr.
Okay, I will probably share it with the guys here, and they can share it with you later.
Actually, I don't see it in the chats.
Okay, so.
Yes, I'll share it. Excuse me, Mr. Abdulrahman.
Yes.
There's some questions in the chat box. If you don't mind, answer it.
Okay.
Okay, read
sorry,
them.
I don't
The first
see.
question from Hanadi Muhammad says, as a reservoir engineer, do you have to be familiar with well testing?
Well, no, it's not necessary to be aware of, or not necessary to be specialized in well testing. We usually do have some engineers are expert in well testing, and we do ask them for specific matters. But for me, to have a general idea about well testing, this adds a lot of value to you as a reservoir engineer, because as I told you, it's a very powerful tool to reservoir characterization. So it's better to have a general idea about well testing, to know the basic things in well testing, but to be an expert, so it doesn't necessarily to be, to take it as specialization, because well testing itself, I think it's enough to be specialized in. Yeah.
The second question, Ahmed says, what type of software which used in reservoir engineering do you suggest?
Excuse me, could you repeat the question?
He says, what type of software which used in reservoir engineering do you suggest?
Okay, each topic in reservoir engineering has got its software. For example, for simulation, we use Eclipse mainly, and recently we use Intersect. For example, in PVT, we do have fluid modeler software. But there are a bunch of softwares. Could be used for each domain or for each topic. And to be a successful reservoir engineer, you gotta choose one topic, and you need to be an expert. But before that, it's good to have a general idea about different disciplines, different topics, and then you choose after that where would you like to stand. But yeah, there are a bunch of softwares, and again, might be a little critical to mention some software names, since they are I don't know. I would prefer not to mention other softwares. Yeah.
Secrets, huh?
Well, not really secrets, but it's to avoid any advertising or something like this. It's better. But of course, I mean, individually, I can share with you each software, what does and what not, and how important it is.
Okay. Muhammad asked, why do you need the co-analysis, which give us only relative permeability, when we can have the effective permeability from testing?
Okay. Well, when I said that the permeability from well testing has more representation of reservoir permeability, that doesn't mean we don't need it for for like reservoir characterization. For example, well testing only gives us an average value, but we do use the permeability that is obtained from core data. We used in capillary pressure. That is, later on we need it for initial water saturation, for example, distribution. So at the end of the day, each technique has got pros and cons. But when it comes to averaging permeability, when you ask me what's the permeability of that well, I would rather to share with you the permeability of that was obtained from well testing than from core. But if you ask me what can I do with the core permeability, of course I told you that it's used for like the relative permeability analysis. It's used for capillary pressure, which is initial water distribution, for so many applications as I have mentioned in this lecture.
Okay, that's it for the questions. Mr. Abdulrahman, again, I would like to thank you and for the lecture, and
okay,
that's it.
It's my pleasure. Thank you.
Thank
Wish
you.
it was helpful to you, and see you in other sessions.
Thank you. See you later.
Thank you. Bye.